Hi, I'm Brian Mullin, and this is Balls Out Physics, episode 4.1, Virgin Galactic, Telecom, and Thermal Radiation. Now, I posted a link in the description below to a video called Space is Hard. It was made by my friend Droidfuel, who's spent a lot of time making videos about some of the stuff, some related things that I've been talking about, and he's also become a pretty good friend of mine. He also has a degree in engineering. We talk a lot, and we both see the same problems with the current model of our world, and so we've been working together a lot, and it's been a lot of fun. And so Space is Hard is all about Virgin Galactic and the struggle that Richard Branson and his company have had achieving low Earth orbit. He also made a video on gravity and the relativity issues, the history of it, and the holes that seem to be in the story, so to say. He spends a lot of time on these videos, so please watch his stuff. It's all pieced together with music and voiceover, and he spends a lot of time doing this, and he says it's a lot of work, and to be honest, it sounds like a lot more work than just standing up here and flapping my gums with a marker. So show him some love, please. Watch his videos, they're great. Need to motivate him to make some more, because they're very good. Great talking points too. And they're usually only about 5 or 6 minutes long, so that's not something you have to sit and pay attention to for a while, like I'm sure my videos are. So anyway, back to his Space is Hard video. A couple of the key things I want to point out are, in 1999, Richard Branson announced Virgin Galactic, and it's a company to basically travel the stars eventually, and he announced shortly after the announcement of the company that consumer or commercial flights, tickets would be available to fly on commercial flights into low Earth orbit as soon as 2007, and that never happened. In fact, they've still never made it. They're having a lot of trouble achieving low Earth orbit, and that's kind of strange because in the late 50s. The Soviet Union was able to put a dog into orbit with no computers, no internet, no prior knowledge, no tons of aerospace engineers out there with experience, and Virgin Galactic can't do it. And then you can go farther and say in 1961, John F. Kennedy announced that we were going to go to the moon, and then 8 years later we did it once and then 5 more times, apparently. And I struggle with that one, but they went to the moon and came back. That is such a huge feat compared to achieving low Earth orbit. Low Earth orbit, or LEO, if you remember from the last video, is where is basically the thermosphere, and where satellites and the International Space Station and all these thousands of objects are supposed to be. And we've been shooting them up there all the time, and Virgin Galactic hasn't been able to do it in 16 years with the internet and all of this experience. Now you could say it's because they're using planes instead of using the ground launch pads, because SpaceX has been able to do it, but SpaceX has only worked with NASA so far, and hasn't offered to bring any of us civilians up into space, which really is unfortunate because we really want to go. There's tons of people on this earth that want to go. Virgin Galactic's already sold a lot of tickets to some very wealthy people, and they still haven't been able to get any of them into space. So I'm struggling with this one as well. And so Droidfield actually recently enlightened me to this. I didn't even think about the connection between Virgin, or the misconnection, as you could call it. The how surprising it is that they haven't been able to get into low Earth orbit. And so I went to Virgin's website, and I found after a few clicks that they claim only 553 people have been into space. That's not a lot of people. 553 human beings ever. There's a lot of human beings in the world right now. That's a small amount of people. We have to trust them that they're telling us the truth about everything they've done. And the majority of them have all held some type of rank, commander, etc. So that means they signed a contract with the government. And some contracts that you sign with governments prevent you from telling the truth even if you want to. Now, that's speculation. I'm not saying that they're liars, but I have a lot of trouble believing that things are in low Earth orbit. So, just putting that out there. It's something to consider. Doesn't prove anything, but it is an issue. So, I also wanted to talk about Telecom, and I will start with GPS, not really Telecom, but they are related. I probably mentioned it before, but GPS is one of the first things you think about when people would tell you that, nobody's ever been to space, that satellites aren't real, and, that satellites would burn up in the thermosphere, things like that. You say, well, how does GPS work? It's the very first thing I thought of, how does my Garmin work? That I don't use anymore thanks to cell phones, but it's supposed to work off of satellites, and I actually have an ATV that has GPS on it that worked way back in the early 2000s, and so I wonder, so that was one of the things I thought about too. How does that work? And when you really start to dive into all this and research the history of GPS, you'll find that during World War II, GPS was actually developed, and it went into service in 1947 before any satellite was launched. And so it actually worked using relay towers. And it could still be working the same way. That is a possibility. But the general consensus is that it works off of satellites. But there is a way it could work without them. And then that leads into, we had satellite phones in the 80s and the 90s. People, usually fairly wealthy people were using satellite phones. We had cell phones with towers too, but there were also satellite phones. They did exist. And then all of a sudden the mobile boom takes off, and, well, actually I think they might have been all satellite, but anyway, the mobile boom takes off in the early 2000s and late 90s, early 2000s, and we start building towers everywhere. And a few years ago I was doing a little bit of telecom work, as we call it, and companies will hire structural engineers the mobile providers hire structural engineers to analyze towers for putting more equipment on them. A lot of times, these companies are competing with each other so fiercely that they're trying to provide more bandwidth to their customers to grow their customer base. And so, they're putting more and more equipment, upgrading equipment, putting more loads on these towers, and to the point where we actually reinforce towers sometimes. The tower is maxed out with the amount of equipment it can support for wind loads and things like that, they start reinforcing the base of the towers and the truss members and everything else, depending on what type of tower it is, to allow for more equipment. In some cases, they even build a new tower right next to an existing tower because we're trying to expand to all these mobile providers. But when I started thinking about this back then, I got into it. I thought it was really interesting at first. And the first thing that hit me is, why don't we just use satellites? We have to cut down all these trees. We have to build all these towers on Earth, and we launch all these satellites into space. There's so many up there. Couldn't we figure out a way to use them, or launch a few more? They seem to be so efficient. We have satellite TV, direct TV, stuff like that. So why are we building all these towers? If we're going to take TV into space, why wouldn't we take mobile phones into space, or the mobile phone service into space? It was very puzzling for me back then, but I just kind of shrugged it off, didn't really think too much of it. And then I got into other work where people are running fiber optic lines through cities to put more antennas up on the roofs of buildings. Just antennas all over the place. It just didn't add up for me, but I figured there must be a reason for it. But now I think that reason might be something else. I'm sure you know if you watched the last episode. So that was very puzzling for me. But in the last episode, in episode 4, I talked about conduction and convection, but I didn't talk about thermal radiation, and I didn't do that on purpose because I had looked into it, and I wanted to see what people said. I wanted to see what kind of rebuttals I got with black bodies and everything we're taught, how things radiate in space, and because I knew I had to talk about that in a separate episode because I wanted to explain the thermosphere and all that, and I didn't want to ramble on for an hour. So. Thermal radiation, I think the best place to start is how it works on Earth before you go into space to talk about it. And I want to start with an engine. I think this is the easiest way, a car engine, easiest way to explain it. Here I have an engine and a radiator, and for you gearheads out there, I'd imagine that this is a 4.0 liter straight 6 out of a Jeep. It's just what it looked like to me after I drew it. So we've got our radiator, we've got our hoses, our rubber hoses that transfers coolant to and from the engine, liquid cool. Almost all cars nowadays are liquid cooled, and so that's what antifreeze. You typically have a mixture of antifreeze and water in your radiator. Typically you just call it coolant that that if you fill your radiator and actually the fluid flows into the engine, and there's water jackets in the engine to allow the fluid to pass all through the engine and absorb heat through conduction, convection, whatever you want to call it, into, absorb the heat from the engine and then send it back into the radiator, where air, if you're driving, if you're moving, air is blowing through the front of the radiator, and the coolant's trickling down through little channels in the radiator, and the cooler air is passing through little slats. I'm going to draw like a front. If you look at it, if you're going to cut a section here, say this is a section looking at it, at the front of it, you would say section AA looks something like this. There's a bunch of little slits. Probably, if you've seen the front of a radiator, it's a lot better to look up a picture than what I'm drawing here. There's some little framing in here to hold all these slits together. The air passes through there, and the waters, or the coolant, excuse me, is draining down through the radiator, and the heat in the coolant is radiating out into the air. But you maybe call this convection, but it is a radiator, and then the heat is being transferred into the cooler air. So then you now have hotter air flowing through into the engine bay. However, since the coolant is, since the engine is water cooled and there's so much cool water in the engine, it keeps the engine cool and keeping it from overheating. Now I forgot to mention there's a fan here, and usually on an engine that's orientated like this, which would be rear wheel drive, you've got a water pump that the engine belts turn, which I didn't draw, but that pumps the water through the engine into the radiator and back continuously. And the fan is usually mounted on the front of the water pump, and the fan is there so when you stop moving, you don't have air flowing through the radiator. There's a clutch in the fan, housing that has how the fan kicks on, or that grabs, and the fan starts spinning and it starts pulling air through the radiator to keep the engine cool while you're idling or sitting at a stoplight. That's basically how a radiator works. Okay? But I mean, even with the cooling going on, the engine still radiates what we call through infrared waves. This is what my FLIR camera measures. It still radiates heat away from it through the air, but not efficient enough so it'll overheat if it doesn't have a liquid cooled system. Now there are some air cooled engines that have just fans, but the engine does radiate some heat to its surrounding environment. Okay, so when you think about that, if you have a problem with your liquid cooling system and you say it's not working as well as it usually does, and it doesn't work so well that your engine might overheat, in what situation do you think it would overheat? Would it be more likely to overheat? Driving in the middle of the August summer heat, if you're north of the equator, or driving in the middle of January in the winter? Common sense tells you, obviously, it's going to be more likely to overheat in August, right? Because there's hotter, warmer air around it. And in January, there's colder, denser, more air, and it's cold around the engine. And if you remember from episode 4, hot goes to cold, so the heat and the greater the difference in temperatures, the faster it moves. So the more cold air there is for the heat to escape to. But you do have one more thing I want to mention is you have an engine compartment around the whole thing. So say there's here's your engine compartment. Goes back to the car, and there's a firewall here. Something like that, and the engine compartment gets hot very quick. It fills up with that radiating heat. So I should have drawn it like this. It radiates out, and then the inside of the engine compartment gets pretty hot, and then everything starts to balance out. And so the liquid going through the engine is actually cooler and keeping the engine cold, and fresh air is coming in from outside the compartment to keep the engine cold. So if you have an old beater truck like me with a dated cooling system that you're too lazy to fix, sometimes you got to drive a couple hours on the highway in the summertime. What you can do is turn your fresh air intake on, open all your windows, and open up the heater vent. Turn the heater on, because the way the heater works is by blowing air, or blowing cabin air or fresh air across your coolant through a steel line or something, and that allows heat to come into the cabin. So when in the wintertime, this is how heating in cars works. So if you're ever overheating and you're on the highway and you don't want your engine to blow up, turn fresh air, turn the heater on. It works really, really well. So, I mean, if you got all the windows open in your car too, it's the same thing as the engine compartment. It lets the heat escape to the cooler air outside. I mean, it's still hot outside because it's summertime, but it's definitely a lot hotter in this engine compartment. So that's a way that you can save your car, your old truck. So that's to give you an idea of how it works on Earth. It does move through infrared radiation, but it's moving through air. The wave. If you imagine like waves in a pool, I still kind of visualize it as moving through the air in that wave, in that electromagnetic wave frequency. If you look at the frequency chart, so this is how radiation works on Earth. Now I'm going to cut and I'm going to draw a new sketch to try to visualize how this would work in space, or how I visualize this working in space, and you can form your own opinion on that. So I'll cut and be right back. Alright, so here's the new sketch. In the center here I have Earth that I sketched up based on the Apollo 17 photograph, which is probably the most famous real picture of Earth. What's very surprising when you start looking into all this is how few real pictures there actually are. All of the new stuff is composite. The new video Earth pictures is composite. You can really tell it's a composite, kind of almost like a rendering, or even cartoon some people call it. I don't want to call it that, or an animation for the newer stuff. And this was supposedly taken 40 years ago. And I've also watched people who are very good with Photoshop play with layers and break this down and show that it kind of looks like this was faked. But I'm not a Photoshop expert, and I'll let you be the judge of that. If you just look into this and see what you find. But anyway, assume it's real. Apollo 17 photo. Got Africa, Madagascar, Saudi Arabia, Iran, and India up here. That's the footage that's in a lot of our textbooks, or the picture that's in a lot of our textbooks. And so I'm assuming that the sun is over here, and it's 100 times the diameter of Earth, so all of the light should be, or the majority of the light should be engulfing Earth, theoretically. And got sun rays, typical. TYP is a very common abbreviation you'll see on engineering drawings. So I've got the sun rays engulfing Earth, or absorbing the rays that are hitting it, and the other ones are passing by. The ISS up here in the thermosphere, and then I've got a blow-up of the ISS that I want to talk about. And also added up to Apollo 13 up here, because I've mentioned it on the last video, and some people had said that the light hits Apollo 13 and it heats up, but it immediately cools down. Heat immediately radiates away because of black bodies and thermal radiation in space through infrared light. Okay. So starting with the ISS, because the ISS does have a cooling system on it that's supposed to cool the I'm looking for solar panels. And so, you know, I kind of looked into that a little bit before I made episode 4, but you know, I figured I would get people commenting about that, about the ammonia-based cooling system. It's a liquid cooling system, just like I described with the engine. Well, not just like I described it, but very similar. And so what's supposed to happen is these are the solar panels right here. If you look this up, I have a link below in the description to a space.com article, or to the space.com description of how this works. And so you've got the solar panels, and then this is the body of the space station, and you've got Russian and American side. You can see all this on space.com. And there's supposed to be liquid ammonia flowing through the solar panels and through piping and everything that comes to these little red squiggly lines here that I've got representing the radiators. Now each one of these, there's 3 at each one of these locations, so there should be 6 radiators total. And so just like with the engine, the car engine, heat is absorbed by the solar panels to keep them cool. You know, heat escapes from the solar panels to keep them from getting too hot, and then the heat flows into the cooler ammonia, and then the ammonia flows to these radiators, and then heat radiates out into space, or the thermosphere where the ISS is. Okay, but in this case it's not the same, because the air particles are so far apart from the radiators that the heat isn't transferred directly into matter. In fact, the heat just becomes electromagnetic radiation or infrared light. That's very different. And what's confusing to me is when and why does heat suddenly jump from matter to nothingness? You know, we're told, and it's accepted, that light can travel through a vacuum. And we can build a glass vacuum tube or a box or something on Earth and apparently shine a light through it, artificial light that we create, and we can see the light passing through it. In my opinion, that's not the same thing. Outer space is not supposed to have a container, and I think the container does affect the experiment. And if you've ever studied the double slit experiment and what happens in that experiment, how do we know that we're not seeing light pass through a glass vacuum tube? Because we expect to see light covering all the electromagnetic spectrum, but we can see the visible light passing through it. Now that sounds far-fetched, and in episode 6 I will go over the double slit experiment because that is one of the most mind-blowing things I've ever discovered in my life. And it'll help me explain why I think this could be different and possibly a trick, not necessarily people trying to trick us, maybe the world actually tricking us, and I'll get into that, so I can't explain it yet. So let's just assume it works. Let's just assume that heat contained in matter, in that ammonia, in the radiators, can just become infrared light and radiate out into space. And since space is so much colder, or the black bodies in space, because this is the theory, that there are black bodies in space that absorb all of this heat, or this electromagnetic radiation, it escapes from the station and it doesn't get hot. Okay? And my first question when I started thinking about this is, what about satellites? Do all of the satellites have these ammonia-based cooling systems too? Because they have solar panels as well. They're going to need to cool those solar panels. So maybe they do. But that's a lot of ammonia-based cooling systems. And have we been using those since we started launching satellites? I don't know. So that's the question there. And then Apollo 13, the argument against why it doesn't get hot is because the light hits it and then it immediately radiates away through. It immediately becomes infrared radiation. And the body of the space station is supposed to reflect that supposed to reflect electromagnetic light so it doesn't get hot, and the same with astronaut spacesuits, etc. That's a tough one for me, but assume it works. Okay? So infrared radiation, or infrared light, radiates away from these little radiators out into the void of space, where theoretically I would say it's infinitely cold compared to everything else. It's theorized that out in space there might be locations where absolute zero is obtained. If you've never heard of this, absolute zero is the theorized temperature at which atoms stop moving. Things freeze completely. The electrons, protons, whatever, the stuff that makes up the atom stops moving. And that is roughly negative 273 degrees Celsius, or 0 Kelvin. We actually have a temperature scale based on this, and that's what Kelvin is. And if you want to convert Kelvin to Celsius, all you have to do is subtract 273 degrees from whatever temperature you have in Kelvin, and that'll be your temperature in Celsius. So just some food for thought there on the idea of absolute zero, which we've never been able to attain on Earth through experimentation, but that makes sense because heat's always going to find its way to what we're working on somehow. But we have achieved some very, very cool temperatures, which is very interesting. So, all right, heat escapes these objects through infrared light. So it's not, the heat just becomes infrared light. That's the way I interpret it. And so here in the thermosphere, where we've got these hot temperatures, I crossed out sphere because I'm not sure what the Earth is, so I'm going to try to refer to these as the thermo layer. because layer works on a sphere or flat or concave, whatever. So then the thermal layer, even though the temperatures are this high, the particles are too far apart, so they don't transfer heat to the station, but they also don't transfer heat away from the station. So they're kind of doing nothing. And infrared light is doing it all. Right? And so somebody actually posted this on my last video. I looked through some PowerPoints, but I hadn't seen this one, and this one I like. It looks like it came from European Space Agency and a college course. But I've got a link posted this below, so you can go through the slide if you want to. And it's 66 slides, but I wanted to focus on radiation here. They go over the means of heat transfer, and then they state that radiation is how it's done in space. So we have the characteristics of radiation, propagation of electromagnetic energy in a straight line between surfaces separated by absorbing, scattering media, which they have crossed out because that's what happens on Earth with the engine example. That's what the air is around the engine. That's what it's considered, absorbing, scattering media. It absorbs the heat and scatters it out to colder areas of the air for heat to radiate away from the engine, or air traveling through the radiator, etc. But then they say it happens or in a vacuum. So in a vacuum, it also works, which is, it's two very different situations in my opinion, but it works in a vacuum. Okay. Hence, without matter displacement. So on Earth, we do have matter displacement with thermal radiation, but in space, we don't. It's totally different, which is somewhat confusing. Okay, and it's reflected, absorbed, or transmitted on surrounding bodies. And so in space, what they do is they assume this idea of a black body is either real or a fictitious surface. So, and my guess is it's generally fictitious because they don't have an actual body they can use for analysis, but it's real or fictitious, and it absorbs all incident radiant energy from every direction at every wavelength. Okay? And so radiated energy depends only on temperature. See that? So that's how it's supposed to work in space. Well, the thing is, we can't test this. The majority of us human beings here on Earth, only 553 people have been able to witness this in action, allegedly. So we have to take their word for it. We can test the car engine, as everyone knows car engines get warm, and you can see coolant flowing through a radiator if you open the cap on a radiator. Now, only do this if the engine is cool or running at operating temperature and not overheating. Never ever open the cap on a radiator if the car is overheating. You may be tempted to do that to cool it down, but you will get burned. And I was stupid and did it once, and I'm very lucky that I didn't get very badly burned from it. I was very young and naive. But don't ever, just if the engine's warm, just don't open the cap. But you can see coolant flow through a radiator, and you can feel heat from an engine. And if you open the hood of an engine compartment, you can feel the heat rush out into the cooler air that's around you. And you can also test cooling an overheating engine with a heater by turning the heater on if you want to. These things work. We know they work, so we can test this on Earth. We can't test this. We can't test electromagnetic radiation, light, hitting objects in space and then immediately radiating off so they don't melt. Okay? We have to take people's word for it. And it's hard to wrap your head around because it seems to be opposite of what happens on Earth. And it seems like as I was explaining the engine example, on a colder day, an engine would be less likely to overheat. But the temperature in the thermosphere is 1,500, 2,000 degrees Celsius. So that's what's strange here is the IR light, infrared light, is unaffected by the temperature of the thermosphere. It doesn't matter. It's all about black bodies and how the radiation wants to travel to these fictitious black bodies that are very cold. Okay? So that's how it works, and let's assume that it does work, that the electromagnetic or the infrared light can transfer heat away from bodies in space. Alright, so now that we went over the space station, get rid of that, I had that blown up view of it. So Apollo radiates away its heat. We know that, or that's what we're assuming, that it works. ISS radiates away its heat. So now, you might be wondering, like I am, what about Earth? Earth, we're told, as I explained in episode 4, Earth gets warm because the atmosphere, the particles in the atmosphere, the air, absorbs light, electromagnetic radiation from the sun, and becomes warm. That heats it, okay? So, light is coming from the sun and hitting this side of the Earth, and it's being warmed, right? And as we know, when the sun goes down, or goes out of our view, whatever you want to call it, the air begins to cool, the ambient temperature begins to drop. And so that would be this side of the Earth. It would be nighttime on this side of the Earth. But if actually, I'll put that back up here. If all this heat right now is radiating away from this Apollo 13 or any other spacecraft or satellite that's in space, then why doesn't it happen to Earth? Once this side of Earth is no longer in the sunlight, shouldn't all of the heat immediately radiate away, just like it does for objects in space? Remember, when we look at the layers of the air, start down here in the troposphere, this is where it's cooling off, where we experience the temperature drop at nighttime. When you go into the stratosphere, the temperature does go up a little bit, but it doesn't get higher than it does in the troposphere, and then in the mesosphere it gets colder. So thermal radiation, from the engine example, you would expect heat to move up into the mesosphere, but then it gets really hot in the thermosphere, so you would expect it to move into these colder layers here and not go into the thermosphere, unless you accept that, or you take the assumption that the thermosphere doesn't affect thermal radiation. Now there's a gray area there because through these layers it's moving through air, and the wave, the electromagnetic wave, is moving through air, and so air is kind of part of the wave. It's scattered. It's scattering meteor. There's matter displacement, as shown in that PowerPoint slide. But since in the thermosphere the hot air doesn't affect the satellites and the ISS, we have to assume that it doesn't affect thermal radiation leaving Earth, or radiated heat leaving Earth, right? It has to be that it can't do one and it can't stop one and it can't stop one and prevent one and allow the other to happen. It has to be consistent. I mean, at least that's what logic tells me. So thermal radiation leaving the Earth is not affected by the thermosphere at all. So what stops all of this heat from immediately escaping? And these fictitious black bodies are very, very cold in space, and we assume that there's very, very cold mass out there in space, and that all of these objects up here, the ISS, the Apollo capsules, whatever, space shuttles, everything immediately radiates the heat away so it doesn't overheat. So wouldn't that happen here on this side of Earth? What's stopping it? Why all of this heat would immediately radiate out of space? This side of Earth would freeze. We'd die. We couldn't survive here if this is what happened. That's just the way I see this, looking at it logically. I mean, even if you make a fire, that heat is gone. It's just immediately, without the sun there warming the atmosphere, we would get very, very cold, just like everything else, right? Just like all the other objects in space. This should all happen the same way. That's very puzzling, because we know one thing we can test is we can go outside at night, and yeah, it's colder, but we don't freeze to death. I mean, in certain parts of the world it's probably pretty cold, but we can put coats on and we can survive. But the ISS, according to NASA, without its ammonia-based cooling system, would see temperature swings between 250 degrees Celsius and or Fahrenheit and minus 250 degrees Fahrenheit. I think it's around 150 degrees Celsius, well over the boiling point of water, and minus 157 degrees Celsius. I said 150 and minus 157, something like that. It's I mean, very huge temperature swings. But with their heating and cooling system, it's controlled. But Earth doesn't have an ammonia-based heating and cooling system. It's just got air around it. And so what keeps all this heat from escaping? You might think, when I first started thinking about this, I thought, okay, maybe some of this heat from over here where it's getting hit by sunlight makes its way over here. But no, space is colder. The black bodies, the assumed black bodies in space are cold. So it would go, the heat would be going this way too. It wouldn't come over to this area. I mean, the heat would just be trying to get away from Earth as fast as it possibly can. So that doesn't make sense to me. So what are we left to assume here? We know it does cool down at night, but not as rapidly as the rest of these alleged objects in space, these alleged satellites. Where's the heat going? That's the question. Well, if you've been following around with my other videos that I made in between episode 4 and this one, then we, the truth-seeking community, this amazing community of people asking questions and working together to try to find the truth for no other reason than to find the truth. Sorry, I'm very excited about that. It's so awesome. But we may have come to a conclusion of where it's going, and I'll talk about that in episode 4.2. So think about this. Where is this heat going? Now, one more thing I want to say, because I still don't, there might be an explanation out there for this, but I like to try to think things through on my own. Why does heat that's contained in matter suddenly jump to electromagnetic radiation, infrared light, where there's no mass? You know, like we said, infrared electromagnetic radiation can travel through a vacuum. We're assuming that is correct, but what makes it jump? And when I really started thinking about this, I remembered the most, I'm sure you've seen this equation before, the most famous equation that we've all heard of, I'm sure, is E equals mc squared. I'm sure you've heard of this equation, right? Everybody's heard of this. What this says is energy, or heat, or the amount of energy contained within a unit volume is actually the definition of heat. People have called me out on that, and temperature is actually the measure of energy in the particles, but semantics, in my opinion. Heat, energy, is equal to mass times the speed of light squared. But we have energy moving through nothing, and there's no mass, because light doesn't have a mass, or sometimes they say photons do have mass, they don't have mass, do they? I don't know, but infrared radiation, does it have mass? But there's no particles in the thermosphere, and as you get into the exosphere and out into space and farther away from Earth, there's very, very few particles, not enough for waves to travel through, so the waves are traveling through nothing, because here on Earth, when electromagnetic waves travel through the air, it's kind of like waves traveling through a pool. Like, you can't see it, but they are moving, they're displacing matter. Matter is being affected by the waves traveling through them. But in space there is no mass. So if mass, isn't mass zero? This becomes zero. 0 times something is always 0. So energy is 0. So heat's 0, well, what? Very confusing. I'm sure there's probably a complicated explanation for this, but this is very simple math here. This equation is very well accepted, especially when it comes to nuclear power. So, what's going on? How can things in space be so different than on Earth? And what I always go back to, yet we theorize dark energy because of the conservation of angular momentum, which we've tested and shown works on Earth. But then some of our laws seem to get defied right around Earth, and it just doesn't add up for me. And so this is why thermal radiation and black bodies and all of this kind of complicated reasoning isn't logical to me. This equation was thought up by Albert Einstein. Most people know that. And Albert Einstein said that if you can't explain something simply, then you don't understand it well enough. Well, the general public, the people that are paying for all of this space travel, all these satellites, we're the ones paying for this. We are asking for explanations for these things that don't make sense for us. And we don't want complicated explanations, and the man who came up with this equation, the unofficial poster boy of science in my opinion, everybody knows who Albert Einstein is. He's probably the first scientist you think of when you say, hey, name a famous scientist. He said that if you can't explain something simply, then you don't understand it well enough. So we need some simple explanations for this. We're tired of complicated explanations. A lot of people haven't had all the math that these scientists have had, and engineers and everybody else. You're throwing out equations with derivatives and integrals and all kinds of calculus, and it just confuses people. They don't want to try to figure out the answer that way. And if you have to explain it with calculus, then you don't understand it well enough. I agree with Einstein on that one. So we have, again, 553 people to trust, the majority of whom sign contracts with governments, and how can we trust that they're telling us the truth? Many people aren't trusting government anymore, and I don't trust the government very much. One of my favorite memes out there is those who trust the government probably didn't pay attention in history class, because governments have done some very bad things to people over the years, and they're pretty much responsible for more death and poverty and suffering than anything else. So why are we trusting government agencies to tell us what our world is? I don't know. Getting too philosophical, I guess. But these are the things I'm struggling with, and this one defines so many simple things, simple equations, simple logical thoughts and reasoning. So think about it, form your own opinion, because this is just my opinion. I'm just giving it to you. I'm not telling you what's true or not, like I try to say a lot. So that's it. Can these things really cool in space, or cool instantly in space, without it happening to Earth too? And if this isn't what's keeping Earth cool, if this thermosphere is really hot and it would affect thermal radiation, then it would keep all the heat in. So then where would the heat go? The heat wouldn't be able to escape, and then these layers would get really hot. Just thinking about this, if the sun is constantly heating the Earth, the heat wouldn't be able to escape. So we would all catch fire, and the whole Earth would burn up. The heat's got to go somewhere, and that's what we'll talk about in episode 4.2. So until next time, keep thinking, keep asking questions. Let's find the truth. Peace.